We're back. All right, today we got hopefully a short lesson, shorter than last time. And we'll start off kind of like with a question that I meant to ask you before the end of the last lesson. And that's your experience with the hottest time of the day versus when the sun's at its highest point in the day. And we learned that the sun's at its highest point in the day around noon, sometime in that area. It reaches its peak. But from your personal experience, you probably know that's not normally the hottest time of the day. And that has to do with something that we're learning in this unit, and so let's talk about it. So note the average hottest time of the day isn't when the sun is at zenith, but in the late afternoon, usually 3 to 4 p.m. Now this isn't always true, but it's usually true, it's the average. And the coldest times are just after sunrise. Also note that the hottest time of the year isn't when the sun's at its highest point in the northern hemisphere, its most northerly latitude point, June 21st, on the Tropic of Cancer, but it's about a month later, in late July. And the coldest times aren't the shortest day of the year, December 21st, when the sun's at the lowest point in the sky. It's actually about a month or so later, the end of January. And this shows that right here, the maximum temperature in July, right there, if you go down, sometime in July. And that has to do with the delay in the time it takes for Earth to absorb energy and then radiate it back into the atmosphere, and for the atmosphere to show that up with an increased temperature. Same thing with the minimum temperature. It takes a while for all this heat energy to be released back into space, and that's why it's coldest here in January. That's the lowest point in the graph. And the same thing happens in the daytime, not just over the year, but the daytime. The hottest time of the day takes a little bit longer for that solar energy, which is absorbed the most around noon, to give back its heat to the atmosphere in the form of infrared radiation and warm up the air a little bit more. And that's why the average hottest time is, in the afternoon. And the coldest time of the day is in the morning, just after sunrise, because that's when the Earth has radiated all its heat back to space, and now the sun's coming up to do it all over again. Just after sunrise usually, because there's a little bit of cooling due to evaporation when that sunlight first hits moisture on the ground. Okay, today's main lesson is on insolation intensity factors. The following factors affect how much solar energy is received by any location on Earth's surface or its atmosphere. And so we're going to talk about different things that control how warm the Earth gets because of sunlight, insolation, incoming solar radiation. And the first one is called the angle of incidence. You can think of this as how steep the sun is in the sky. The steeper the angle of insolation, the sunlight, the more concentrated the solar energy becomes. And so here we see this ray of sunlight hitting the Earth here versus here. And you'll notice this area is a smaller area than this area. And this is a more direct sunlight right here, whereas this is more oblique. It's at a shallower angle. And you know what times of year and day the sun does this. The sun's at its highest point in, around noontime, and during the evening and the early morning, it's more oblique or more spread out. And during the year, the summertime, sun's higher overhead. And in the wintertime, it's lower, producing this more oblique angle. And so different times of the day and different times of the year kind of work in concert to give us warmer temperatures, either throughout the day or throughout the year. And you can see that right here. Here we have a flashlight shining on the surface, and you'll see intensity is light over area. And right now we have 2 units of light over an area of 2.92, and that comes out to intensity of 0.68. That's a low sun angle. Now we can drag this up, and you'll see as it gets a little steeper, the light is still putting out 2 units, but the area is getting smaller. The little area where it's hitting is getting smaller. And you'll see that's making the intensity number go up. Now we're at 1.88, 1.93, 1.97, and now we're at the highest intensity, and you notice the area is the smallest where the sunlight is hitting. Once again, going back, you see the area gets bigger, smaller. It's spread out over a larger area, more concentrated over a smaller area. And that determines intensity. This happens throughout the day, morning time, towards noon, back to the evening. And it happens throughout the year at any given time of the day. For instance, certain times of the day, depending on where the sun is, or the earth is around the sun, you're going to have a steeper sun angle versus a shallower sun angle at the same time of day. Okay, next insolation intensity factor is the duration of insolation, the length of sunlight. The longer the Earth's surface is exposed to sunlight, the warmer it gets. This is a no-brainer. And if you look, we'll pick a latitude similar to us. Let's see, we have 70, 60, 50, so we're somewhere in between this red one, just below this red one, kind of like that. And the main thing you want to take away from this is that we have different lengths of daylight depending on different times of the year. And we already talked about this in the last lesson on seasons. And you can see the 16-hour line is right here. We're just beneath that here up in here in Fort Plain in New York. And in the wintertime, we're just above 8-hour line. But if you're at other places on Earth, I mean, look at the North Pole, or close to the North Pole, 70 north. You get a lot of sunlight in the summertime. But it's still kind of cold there. But it'd be a heck of a lot colder if that sun wasn't up. The reason why it's not super warm, even though they have 24 hours of daylight up here and below and above, 24 hours of daylight, is simply because the sun's still really low in the sky. So if you think back to that last slide, it's spread out over a greater area, all that sunlight. So it's not as concentrated. But you know, places like the equator, they have 12 hours of daylight all year. Doesn't matter what day. And you know, it kind of makes the days the same length, so they're always getting a good deal of sunlight. And even though the sun's not always straight overhead at the equator, only a couple days of the year, it's still, on average, the most direct insolation there. And that's why it's very warm. Any other interesting observations about this graph? One thing I always like to point out is how they all kind of intersect on these dashed lines. And if you look closely what those dashed lines say, they are the March and September equinoxes. They're the equinoxes, first days of spring and fall. And remember, equal day, equal night, everywhere on Earth. Okay, third insolation intensity factor, atmospheric transparency. This is really what it sounds like. Transparent or clean air allows greater amounts of sunlight to reach the Earth's surface. So during the daytime, this will heat things up. But other factors can decrease transparency, like dust, smoke from forest fires, like you see here in Yellowstone Park on the left. Volcanic ash in the atmosphere diminishes insolation, lowers the insolation, blocks out sunlight. So these things produce a cooling effect when there's a lot of these particulates in the atmosphere. You know, those major volcanic eruptions really do lower the temperature of the Earth. Speaking of that, 1991, Mount Pinatubo erupted in the Philippines, and all that ash went flying up into the atmosphere, the troposphere and the stratosphere. Jet streams circle it around the Earth, and we have a cooling effect because of that. It blocks out sunlight. And you can see that in this graph showing the average temperature of Earth over time, and there are, of course, ups and downs, but there's the eruption, and you can definitely see major effect. Look at how low it is right there compared to normal. And then that ash will eventually settle out of the atmosphere, and things will return back to normal, which really isn't normal, but it's not as cold as that point. All right, so this question here, explain how the volcanic eruption could have caused the general decrease in temperature shown by the graph. It blocks out sunlight. So that would be an answer, but you'd want to state a little bit better than that. You could say that the ash from the volcanic eruption is blocking sunlight from reaching the Earth's surface, something like that. Okay, the next question, which change would cause a decrease in the amount of insolation absorbed at Earth's surface? So decrease the amount of sunlight hitting the Earth. An increase in cloud cover would cause that, so it can't be A because that's a decrease in cloud cover. A decrease in the atmospheric transparency, that means making it less clear. Decrease the amount of insolation, yeah, that might be it. An increase in the duration of daylight. Nope. And an increase in nitrogen gas. Now, nitrogen is inert. It's really not affecting anything. We breathe a lot of it in every breath, and it's not doing much. It's clear. So the answer has to be B. Okay, the fourth insolation intensity factor, and then we are done, is kind of like a combination of some things we've already learned about. Color, remember dark versus light colors. Dark absorbs, light reflects. Texture, remember that rough textures absorb more because they have more surface area than smooth surfaces. States of matter, liquid water can absorb more energy than ice or water vapor. And specific heats. Certain substances can absorb a lot more heat than others. They absorb it more quickly than others. And so those have minor effects too. All right, some graphing. The intensity versus angle of incidence. That's the angle that the sun's coming in at. And if the sun is coming in at a steeper angle, it's going to be more intense sunlight. The next one, duration of insolation. That means length of incoming solar radiation, the length of sunlight. So longer days, and that's going to be more intense. And transparency. It means how clear the atmosphere is. The clearer, the more intense. So just keep an eye on these types of graphs. All right, another term, albedo. We already talked about this a few lessons back, but it's the fraction of solar energy reflected back from Earth to space. It's a measure of the reflectivity of our surface. And if you look at these diagrams or these pictures, you'll see that Earth's albedo, or reflectivity, changes from top to bottom. And if you can't see it, the top is December 3rd through February 4th, and you can see it's pretty bright, like there's snow there. And then March 4th is the next picture down, June 4th to August 4th. You notice there's a lot darker colors on Earth there. And then starts to get a little bit brighter again on the bottom picture, September 4th to November 4th. And if you guessed the seasons, you're right. This is snow melting from the top towards summertime in the middle, and then reforming again at the bottom. So that snow actually makes the Earth, or the sun, reflect off the Earth much more. So albedo changes throughout the year because of the seasons. And there we have albedo. More reflection is towards the poles, if you haven't noticed that. The darker red there in the key shows that. Look at all the reflection in the Sahara Desert. Perhaps you can think of a reason why that's so. Same thing with Saudi Arabia. All right, so there's a quick lesson on some insolation intensity factors. Next lesson, we're going to talk about climate control factors. So I'll see you back there then.